All right, so what we're going to talk about today is Dynamo. So Dynamo is a way to scale and serve generative AI fast. So what does this mean? Basically, it means, there's a lot of tips and tricks, right, to serving large language models, and Dynamo kind of, rolls those all into one thing. So the idea of Dynamo is to allow devs to focus on deving instead of focus on, a bunch of really technical minutia, worrying about what network they're on, how the models, leveraged across that network, how everything to do with these kind of more complex, systems that we're going to talk about. Dynamo is meant to make that easier. So before we kind of get locked into the world of what Dynamo is, also I'm Chris Alexiuk. I'm a product research engineer for deep learning at NVIDIA, and Dynamo, of course, is a thing that we do. Okay, so before we get too bogged down, we have a small agenda here. So how LLMs work, model serving techniques, data scale inference with Dynamo, and the Dynamo architecture. And we have some time for some Q&A at the end. So how LLMs work, this is probably clear to a lot of people, but we'll just make sure that we all kind of understand. And basically, LLMs at their core are machines that take tokens and then they spit out tokens. Now, this is, an example of the kind of most basic, LLM, inference, which is this idea. This is autoregressive inference, right? So this is how LLMs produce tokens. This is why people kind of make a meme that they're like a next token machine, right? So, but the idea is, right, that this is the part of whatever we're dealing with LLMs. So basically, we have some input tokens. We generate a new token. We use that new token, right? We add it to the end of our existing tokens, and then we use all of that to predict another token. And we keep doing this forever. We take the output of the model and we feed it back into the model. So auto, right, and regressive. We just keep doing this auto-regressively, which is great. I mean, we've done this for a long time. It's great. It's great. One thing you're going to notice though is that we only actually attend to new, previous tokens. So we never care about new tokens, right, until we start thinking about the one after that. Something else you might notice is that the previous tokens are completely unchanging, right? So in the example we saw of Rick Astley's "Never Gonna Give You Up," never gonna stayed the same the whole time, right? So this is like a little area that we can exploit because we know it's never gonna change. So what do? Well, we add this idea of what's called a KV cache. Now KV cache, K and V from QKV from the transformer architecture, so key and value, is basically a way that we can save some compute at the cost of memory, right? So instead of thinking about the idea of every single time we compute every single piece of attention, right? We only care to quote unquote do the new calculations, right? Because the KV cache, or because the input, never changes, at least a chunk of it, right? The initial context never changes. We can kind of just compute that once and then use that for the rest of our time. Now, this does cost memory, right? So it's not free. It's not like we get a free lunch here, but it's much more efficient from a compute perspective. It computes the thing that's bogging us down a lot of the time. So again, we trade this memory for saving ourselves quite a bit of compute. But the math is pretty straightforward. We're not going to go into it here, but the idea is, we have this sequence, we compute it once, we store it in the KV cache, and then as we add new tokens, we use the KV cache plus computation for the new KVs that we get from this new token that was generated in the previous step, and then we continue to append it to our KV cache. So one thing that you may notice is like your KV cache can continue to grow for a long time, right? But it doesn't have to continue to grow. It can, in fact, just stay as this one piece. In fact, we can programmatically define what it's going to be, which is extremely useful. We're going to talk a lot about that in just a moment. Because there are two phases, right, to inference. We have the pre-fill, and then we have the decode. So pre-fill, right, is our context. This is our initial query. This is whatever stuff we've passed to the LLM, right? This is going to be what's pre-filled. This is the active. We've got to move the we have to move the data from somewhere to our GPU in a way that it's ready to be consumed and ready to be leveraged as part of this autoregressive loop that we're talking about. And then, of course, our decode, aka generation, aka sampling, is basically talking about that autoregressive loop. So that we're generating a token, we're generating a token, we're generating a token. This is the idea of pre-fill, which is whatever we start with, right? And then decode, which is whatever stuff our LLM is producing. We're gonna, it's important to draw this distinction now because we're gonna again leverage the idea of this with Dynamo. So why do we care about these things from like a performance perspective? Well, basically our pre-fill is going to, limit us in some capacity by our time to first token. So all that time we spend pre-filling, we're not generating a token. And then of course our decode phase cares about, this tokens per second metric, which way that we can think about that is through inter-token latency. So how long between each token? And one thing that's fantastic about these networks is that like this time should be relatively standard between tokens, especially for leveraging the KV cache, right? So it shouldn't take more time to produce the last token than it does the first token, due to the fact that we're being clever about what we're saving. Now, our time to first token is how quickly do we start, right? So that's very like user impacting, and then ITL is also very user impacting to a certain degree, right? To a beyond a certain point, it's just very fast. Why is this important for agents now? Well, remember when we have two agent systems communicating with each other, the faster that they produce tokens, the faster that they can communicate, right? So all of this kind of stuff we're going to talk about today very much drives how efficiently and effectively our agent systems can work. And we're going to talk about kind of a little extra reasons why as we get into the more Dynamo specific slides. But this is kind of like the overview of how LLM go burr, right? So we hopefully we get it at this point. But the idea is that we care about these two phases. And the other idea is that we care about this idea of a KV cache, basically just letting us skip some compute by trading memory. So we have some serving techniques that are kind of normal. We have this idea of batched serving. So this is pretty classic, right? You have static batching or you have continuous in-flight batching. Static batching is an excellent way to approach things. In-flight batching is going to be able to, keep those GPUs churning, right? So keep our GPUs kind of, smashed throughout the, throughout the inference. You'll notice that with continuous in-flight batching, right, we no longer stop using our GPU. We continue to smash that GPU for as long as we can. So excellent kind of, approach here. Now, we also have, of course, different compute patterns for prefill and decode. So what you're going to notice is that it kind of, skipping over all of these beautiful matrix diagrams, the idea is that, our prefill is a different method of compute, right, than the actual decode strategy. So as in, it has different costs and uses different operations to do prefill versus decode. Now, this is important because if they have two different patterns, we if we're constantly switching between them, you can imagine now there's some kind of inefficiency that's going to start creeping in, right? And so what we care to do is to disaggregate. We're going to see this word a lot, disaggregate. We're going to see it a lot. But the idea is that instead of aggregating, right, which is where we're collecting things together into one big old group, we're going to disaggregate, which means we're going to spread them out. So, right, typically when you're on when you're using like Transformers library, right, and you use your model, right, you do inference on it, it's going to be aggregating prefill and decode. And effectively what that's going to do is it's going to introduce at scale some inefficiencies. And this is why we care about this idea of disaggregating prefill and decoding stuff. Again, what we want to do is find balance here, right? We want to find the correct balance between what we're prefilling and what hardware we're using to decode. And again, this is a complex process. We're going to talk about a tool that makes it less complex, of course, but this is the idea of disaggregation. So we know that there are different parts of this flow that our hardware is good at, and we want to make sure that our hardware is being utilized most effectively in order to reduce these inefficiencies by having them switch back and forth. It's just not a great time. There you go. And then, of course, we have KV cache reuse. Now, this is a big one. This is, if you read like the Devon team's blog on multi-agent systems and stuff like that, right? They talk about KV cache a lot when it comes to context engineering and agentic systems. And this is because, our KV cache is not like, it doesn't have to be ephemeral, right? In fact, there's many situations where we want it to be kind of persistent. And we want it to be, available to us, and we want it to be available across different, GPUs, so across different hardware. When we're doing something like RAG, and we have a vector database, and we see that one or two chunks from our vector database are over leveraged, so they're used all the time, right? We want to be able to say, hey, actually, let's just leave that in KV cache, right? Because, we know we're going to need it most of the time. And especially as we get into these more complex setups that we're going to look at, this is useful. Things like our system prompt, right? If we have the same system prompt across our application, like why would we ever not have that in KV cache, right? We know we're going to need it, so we should keep it around. This is the idea of KV cache reuse. So it's not just like one time. We should be able to do this many times, and so we should save it, or we should keep it around. Okay, so that's all context. Right? So we've loaded you guys up with context. LLMs go further, they're autoregressive. There's a prefill, there's a decode. Prefill and decode aren't the same operations, so doing them on the same hardware is a little bit slow. It's not allowing us to take advantage of all of our sweet GPUs as well. We also have this idea that KV cache can be reused. All of these things are context for Dynamo. Welcome to Dynamo. So something else has happened that I'm sure you guys are all very used to by this point, which is that test time compute, test time scaling has been popping off, and that means the GPUs are really chugging through tokens, right? If you used any of these thinking models, from the smallest like NVIDIA Llama Nemotron Nano, all the way to the largest, like your O3s Pros, right? These models generate a ton of tokens for a ton of people, and so this becomes something that we have to think deeply about. So more compute memory requirements, challenging with scaling techniques, inefficient routing, and dynamically changing workloads are some of the challenges that we're currently facing now. Again, thanks to the proliferation of test time compute, test time scaling. So what is Dynamo helping to do? Well, it's basically giving us one framework to do all of these things at once, right? So instead of just being a kind of, one-trick pony. This is actually meant to pull in a number of different techniques and a number of different approaches, right? And so we have things like, better routing, lower latency transfer of data, right? Which is, we're going to talk about why these things are useful in just a moment. And then, of course, disaggregated serving is the big one. And again, just to remind you, if you just popped in here, disaggregated serving means we're splitting apart function across hardware. So instead of having hardware that's doing everything, we want to allow our hardware to focus on one task, at a time. There you go. Okay, so disaggregated serving, a classic, right? Instead of just doing this on each GPU, right, where we have this prefill, this compute bound, decode, memory bound, we're going to go ahead and do this on separate GPUs, and then we're going to think about parallelism for each of those separately, right? So instead of it's not like a one-to-one, right? Or we actually get to choose, well, how much are we pre-filling, into our KV cache? How much hardware we're using to decode, right? And we're able to choose that balance between the two fairly straightforwardly, right? So choose which one is like the fastest. It also allows us to think about what kinds of hardware are doing what jobs, right? So as in, the decode job, we might be able to use like typically slower GPUs. We might be able to use smaller GPUs and maintain performance versus that pre-fill phase, which we might want some big bad GPUs, right, with loads of memory. So this is better for big models. When you have more GPUs, of course, if you just got one GPU, disaggregated serving is not going to be a super, incredible thing for you. And then very long input sequence versus the output sequence. When we're decoding a lot of the time, these approaches are going to be more similar. So that's the idea, right? And again, we get to choose both how much we scale out each of these independently, and then what kind of hardware we leverage for both, which is excellent. So you see this, we have, on one node versus two nodes, with our baseline versus the disaggregation. We have some beautiful Pareto fronts here. And the idea is that the disaggregation pulls ahead pretty straightforwardly. And again, this is at this ideal condition where we have kind of this, long ISL, so that's input sequence length, and then a relatively short output sequence length, right? So this is for things like we have loads of context, we have a big system prompt, we're doing something like RAG, we're doing something like storing a lot of conversation history from our previous turns. So we've had an agent system running for a while, and as you can see, this disaggregation in these conditions just kind of smashes the non-disaggregated method of running this. We also have something called KV cache aware routing. So remember, right, KV cache is important because it makes us go fast. And when it comes to choosing which of the or choosing which hardware to run on, well, some hardware is going to be we're effectively going to say we want to go to hardware that is highly matched with our KV cache. So how much stuff already exists? How much work has already been done here? Let's think of it that way, right? And the idea is that because we have done this disaggregation, right, and because we're parallelizing across multiple pieces of hardware, right, there's going to be like a best answer here a lot of the time. It doesn't have to, but a lot of the time. And the idea here is that instead of going to a KV cache that perhaps is like, well, the load is pretty low, so typically we're just going to go to the low load GPU. Now we can think about a trade-off, right? So okay, the load is low here, but I am like it's got everything I need already in the KV cache, right? And what this allows us to do, again, is make things faster. So instead of just considering the fact that we have this, kind of like traditional load-based routing, we can now think about KV aware. So it's not just dictated by the KV cache. Match, of course, is also going to be incorporating, load. But again, the idea is that if we've already got most of what we need on a GPU, then we should think about going there before going to one that has nothing that we need or close to nothing that we need. And so this is how this KV cache aware routing really effectively allows us to make things faster. There you go. We love that. The other thing is, right, so as I'm sure you're all aware, there's many different kinds of memory, and many different kinds of memory means that there's different speeds of memory, which means that there's probably like a fastest memory and then a slowest memory. And what has been traditionally true is that the slowest memory typically has very large capacity versus the fastest memory, which has smaller capacity. So we have less super fast memory, we have more slow memory, right? And what we can do is we can do things like leverage that the capacity of the different memories that we have, right, to make this a little bit this system a little bit better. And what that winds up meaning is that we don't have to shove everything into one piece of memory. We can actually dynamically fetch and retrieve the needed pieces of information when we need them from, again, this hierarchy of memory, right? And so what that allows you to do is things like offload KV cache to slower memory when it's not needed, and then prefetch it onto the correct piece of information. And we're actually, this is a classic, if if you've been around the optimization space, a classic thing that allows us to exploit this is that there are things that are going to take fixed units of time in these processes. So one of these things is tool calls, right? So it's going to take some amount of time, and we can actually leverage that time, right? Instead of just kind of leaving our memory filled up during these periods of time, we can actually leverage that time to hide memory and then bring it back when it's time for a response. So this is very classic. We're effectively using that downtime to do more work, and that's why thinking about memory is so important. Then, of course, we have transfer with Nixle, and this is going to be between nodes, right? So we need to make sure that we're sending information around well. We need to make sure that we're transmitting or broadcasting the KV cache to the correct hardware. And the way that we do this is with Nixle. Very straightforwardly, it does it very fast. And so this is going to help us because it's going to make sure that what we need is where it should be when we need it. So where are we at today for Dynamo? Well, it's Apache 2. It is publicly available. You can find it on GitHub at NVIDIA Dynamo. It serves 3 different backends between TRT, LLM, VLM, and SGLang. You have that disaggregated serving with TRT, LLM, VLM. You have that KV cache aware routing with TRT, LLM, and VLM. And then, we're working on a lot of extra stuff as well. But this is the idea for Dynamo. That's about the Prezi that we've got for you today. So the idea is, again, agents require a lot of context, and they require a lot of dynamic context. Dynamo helps make sure that our context is both in the right place at the right time. And it does this in a way that's fast and efficient. And then additionally, that it's being consumed as effectively as humanly possible, again, through these processes like disaggregation and making sure that we're doing our pre-fills correctly. Dynamo makes inference go burr, and therefore it makes agents go burr. I've been Chris. There's my time. Let's go. So if there's any questions, I'll be happy to take those. I think if you can click on the dots, and then so the little dots menu in the bottom right-hand corner, and there's going to be like a meetings tool window that pops up, and you can go to Q&A. You can type your question. I see you have one from Nadia. You have examples where the agents become cheaper by using this framework compared to yes. So it's interesting, right? So the question is, do you have an example of trade-offs when the agents become cheaper by using this framework compared to the single aggregated classic solution? Try to decide the size of the agent system that Dynamo is targeting. This is interesting, right? Because it's not so. We have to disaggregate in our minds the complexity and size of the agent from the complexity and size of our hardware infrastructure. So Dynamo is more so when we have complex, not complex necessarily, but when we have more than a node of hardware or in that scale. And regardless of the complexity of our agent, right, it's actually going to be faster so long as a few conditions are met, which is why we have context. That context is reused, and there is more context than there is output, right? So this is true of most agent systems. A lot of agent systems are going to take in a ton of context and actually return really straightforward, sometimes like 6 or 7 field JSON responses, which are quite small, right, in comparison to the amount of context you're using. And so as long as those conditions are met, then you're going to see some acceleration from Dynamo thanks to this disaggregated approach. But excellent question. When you're on that kind of like single hardware or single node, you're going to find less performance from Dynamo out of the box. Yeah, there you go. Yep, excellent question though. Again, any other questions, you can just pop them in the Q&A feature. Yes, we also have, of course, there's infinite slides. I got slides for days here. If you wanted to look at even more slides, but we do have like an example, right, which is kind of the fun part. So this is just how many steps it takes to get dynamoing. And you can see that it's not many steps. So basically, you can install this from PyPy. Then you can use Dynamo Run. Dynamo Run is a command that's going to, unsurprisingly perhaps, run Dynamo. Dynamo Serve will help us then serve it. Build will actually build a container with all of the dependencies that we need for our solution, and then deploy is how we shove all of that goodness to Kubernetes, to K8s. And again, this is just five CLI commands. They work pretty straightforwardly. Yes. Okay. Well, I've been Chris. Thank you so much, guys, for coming to my TED Talk, and we will see you in the next one. Enjoy the rest of your time at this excellent event that the folks at TMLS and GenAI World have put on. Thanks so much for your time, and have a good day. Bye-bye.